Chapter 14, Statistical Process Control. The Orange Avionics Company manufactures instruments and navigation devices used in aircraft, including altimeters that provide pilots with readings of their heights above sea level. Pilots and passengers have been killed in crashes caused by wrong altimeter readings that led pilots to believe that they were safely above ground when they were actually flying dangerously low. Because aircraft altimeters are so critically important to aviation safety, their accuracy is carefully controlled by government regulations. One of the Federal Aviation Administration, the FAA, specifications is that an altimeter must give a reading with an error of no more than 30 feet when tested for an altitude of 2,000 feet. At the Orange Avionics Company, 5 altimeters are randomly selected from production on each of 20 consecutive production days, and Table 14.1 lists the errors in feet when they are tested in a pressure chamber that simulates an altitude of 2,000 feet. In this chapter, we evaluate this altimeter manufacturing process by analyzing the behavior of errors over time. So let's just quickly talk about a little bit of context here. Now, we don't need to say too much about the importance of an accurate altimeter. We can understand what can happen if planes fly too low. We also know that this altimeter's accuracy is especially important as we get close to sea level. Now, commercial planes or commercial jets really generally fly at about 35,000 feet, which is a little bit above about 7 miles up in the air. So this 2,000 feet, again, is just for landing and takeoff, which is really especially important. And the reason they fly so high is just because 35,000 feet is about that perfect balance where the planes face less air resistance, but they still have enough oxygen for their engines to run. So anyway, so we are testing the accuracy of these altimeters at 2,000 feet. And let's look at our chart here. So for 20 consecutive days, 5 samples were randomly taken, and they put the errors of these samples in this chart. So for -1, for example, the actual altitude in all of these cases was 2,000 feet. That was just taken from putting these in a pressurized chamber. This first sample of day 1, that means that it gave an actual reading of 1,999 feet. Second sample gave a reading of 2,007 feet. Same with the third sample, and so on. So again, we're just looking at the errors. In this chart, we also have a list of means, and this list of means is just the means for all of the 5 samples from that day. And same applies for the median, range, and standard deviation. So now 14.1 talks about control charts for variation and mean. So we're going to explore these different types of charts. Run charts, R charts, R really just stands for range, and X bar charts, which is just the mean, to monitor characteristics of data over time. We can then use these to determine whether or not a process is statistically stable. You can also say within statistical control. So we're going to be using this word statistically stable a lot. We'll talk about what that means. Process data, this is just a type of data here. It's data arranged to some time sequence. They are measurements of characteristic of goods or services that result from some combination of equipment, people, materials, methods, conditions, etc. So question, does the table labeled aircraft altimeter errors contain process data? Why or why not? All right, well, let's look at this data. First question, is it sequential? So does it go through some time sequence? And the answer to that is yes. This goes by days. It goes from day 1 to day 20. So it does follow some sort of time sequence. Second question, does it measure a characteristic of goods or services that results from some combination of these different factors? So what does this chart actually measure? It measures the error in these altimeter ratings. So yes, it measures the quality of these altimeters essentially. And so we can conclude that this data is process data. Let's just write that down. So process data is just the type of data. Now for the different types of charts. We've got our run chart. It's a sequential plot of individual data values over time. One axis, usually the vertical axis, is used for the data values, and the other axis, usually the horizontal axis, is used for the time sequence. And that makes sense that the horizontal axis is used for the time sequence, because we remember that time is usually independent, and the independent variable goes on the horizontal axis. All right, the figure below is a run chart constructed from this data from the first page. So we're going to look at this run chart, and we see that we have 100 observations. Let's look up at this data. Now we have 20 days, but what this run chart is doing is it's taking all 5 errors for that day and plotting each as a separate point. So, the first data point is going to be -1, 1, -1. The second one's going to be 2, 7. Third one's going to be 3, 7. Fourth is 4, -1, and so on. So we're just plotting each of these as 100 individual points in order. And we're looking for any kind of trends in the data here. So we're noticing that these zigzags sort of represent the variation from point to point. And as we go over to the right, as our number that is assigned to each of these data points gets larger, so as we get closer to day 20 than day 1, we can see that we have these really big zigzags. And because each of these points is just a data point, we can see that our variation increases over time. Now, if our variation increases over time, you'll see that we have these peaks here. So look at this point, for example. Well, this point almost has an error of 50 feet. We wanted an error of less than 30 feet. So this point is showing us that that actual altimeter is not up to specifications. But more importantly, this is only day 20. As we go further and further to the right, so after more and more days of producing these altimeters, we can expect this variation to continue to increase so much that almost all of the data points are not within the required specifications. So, yes, the company should be concerned, especially if this trend continues. And so we can write out this conclusion. Now we've reached sort of our buzzword for chapter 14 here, which is this definition of statistically stable. So a process is statistically stable if it has only natural variation, with no patterns, cycles, or unusual points. So there's always going to be variation. In fact, if there's not any sort of variation, that's just a little bit fishy. So a run chart with no obvious patterns suggests that the data are from a process that is statistically stable, and the data can be treated as if they came from a population with a constant mean, standard deviation, distribution, and those other characteristics. All right. If data violate one or more of the following criteria, this is an indication that a process is not statistically stable. So if, for example, there's some type of increasing variation, so as this chart goes from left to right, the vertical variation is increasing. It does not necessarily mean that our mean is changing, but there's just an increase in variation. And this is a prime example of that, where we see this increase in our sort of zigzaggy pattern here from left to right. Now, if we look at the actual mean of error, which is this red bar here, we notice that the mean very well might not change from left to right. But while the mean stays the same, the increase in variation can cause this to be not statistically stable. So this process is not statistically stable based on that run chart. Now we have data with an upward trend. It means that these points are rising. The values are increasing over time. Same with a downward trend. These points are falling from left to right. The values are decreasing over time. If either of these happens, this process is not statistically stable. An upward and a downward shift just means that these points are either lower or higher in the beginning than the end. We don't necessarily have to see that smooth transition from low to high or from high to low that we would see in an upward and downward trend. There can be some sort of drastic shift there. We also have an exceptional value. So if there's a single point that is exceptionally high or low, and we're going to define exceptionally high or low today, then this is not statistically stable. And if there's any kind of cyclical pattern, then this is not statistically stable. One thing to point out is that cyclical patterns do not include seasonal patterns. So take, for example, something like sunscreen sales. Sunscreen is a seasonal commodity, so we can expect that any given retailer will sell significantly more sunscreen in the summer months than in the winter months. And remember that what we're really measuring here is the statistical stability. So we would be incorrect to assume that sunscreen sales, for example, the process of creating a given sunscreen is not statistically stable just because its sales are affected by seasonal factors like the ability to go outside for long periods of time. Let's look at a couple examples of these data patterns. All right, this first graph, we can tell that, it's not a great graph. We've got different days in May of 95. We don't know our units in the y-axis. This is not labeled, so we could do better. However, this does give us enough information to notice some of these graphic trends here. And I'm going to look at two particular sections. I'm going to look at this section, and I'm going to look at this section. All right, the section between the two blue lines. I'm seeing kind of what looks like a linear pattern. It has a slightly negative slope, and the points are fairly consistently spaced apart. And so this is going to be this downward trend. And in this downward trend, these values are just sort of slowly decreasing over time. So now in this green section here, we have all of these points that are pretty consistently around, 84, whatever our unit is. But then all of a sudden we have a jump up to a value of about 95. Then we have other jumps up here to these values over the 100s. But let's stick to just this main jump right here. With this jump, because it's such an extreme jump, these 2 points are much further away from these 2 points. Well, this is going to be an upward shift. And there very well may be different points of variation in a graph where it's debatable whether or not that is a trend or a shift. However, what you should be able to determine is if, for example, we were given these two sections and told one is a trend and one is a shift. You should be able to identify those two. All right, one more down here. This is a slightly better graph, especially considering that we have our y axis labeled, and as well as our x-axis. So this is monthly housing sales in millions with years in the x-axis. And we see that each of these tick marks is a span of 5 years. And now I can see that this data is seasonal. I know that because from 1975 to 1980, 5 years has passed. Well, I see 1, 2, 3, 4, 5 peaks there. I see the same thing in general from 1980 to 85, 85 to 90, and 90 to 95. So in each of these 5-year increments, I will generally see 5 peaks and valleys. And that's how I know that this has some sort of seasonal trend. But what I also know is that if I look past these sharp peaks, these sharp zigzags, and I'm just looking at the general trend of the data, maybe just draw this curve here to show the general trend of the data, I see another type of pattern. And because I see some sort of wave, I see some fluctuation from down, then up to down, then up, then down, then up again. And because that is not a variation within seasons of 1 year, because if I were to look at this as some sort of, I don't know, trigonometric curve, it would have a period of greater than 1 year, then I could say that this also has a cyclic pattern. So this is seasonal within cyclic. All right, now we've got these different types of variation. Random variation is exactly what it sounds like. It's just that variation due to chance. We said earlier that we want to see some sort of random variation that gives us a hint that our statistical methods for collecting this data are valid. So random variation, our goal here is to try to not make a conclusion that a system is not statistically stable due to random variation. However, we should find any assignable variation. And in real life, in quality control at any business, that's exactly what the data analysts are looking for. They're looking for some assignable variation so they can essentially fix the problem. So that just results from causes that can be identified: defective machinery, untrained employees, poor sales marketing techniques, different things like that.